Hi everyone. So this is gonna be the first video on the unit of equilibrium now. And this to me is where I think chemistry gets really fun because now you're looking at reactions and you're saying, okay, if I have these conditions and if I change this temperature, if I change the pressure, if I do whatever, how will this reaction like adapt to it? And I think that's sort of thinking of like, I have this thing, I change it, what happens? I think that's sort of the beauty of chemistry and where chemistry really starts to shine as a really fun material. So hopefully you all love it. I will say though, like at least going forward for this chapter in particular, I'm gonna break up the videos into one of just lecture content and then one of just practice problems. I tried recording this like as a whole video with both, and it was almost an hour long. And I was like, you know what? I'm not making anyone suffer that long listening to me yap. So I'm just gonna break it up and hopefully keep that same format going forward. But yeah, if you just like look in like the little playlist thing of like this chapter, you should see like a video that's just like doing practice problems on equilibrium. So go to that if you want some practice problems too, but this would just be lecture content. So yeah, let's just go ahead and get started. So kind of the first thing I want to talk about with equilibrium is just imagine you have a reaction of two things coming together to form some new thing. It doesn't need to be super complicated, it can be like maybe A and B just formed a new bond and they became this other thing called C, right? You can just imagine two things coming together and just forming a new product. What happens also, and it's very possible, if you just form that one bond, it's very easy for that bond to break, whether it be through a lot of collisions or it's a really hot reaction. That C compound can just break up back into A and B. So while we commonly talk about reactions as just being, oh yeah, you put A and B together and it makes you C, there's also the fact that C can break down and become A and B again. So because of that, you will commonly see these reactions written out as A plus B with these equilibrium arrows. And this is really important, I will say, for anyone taking organic chemistry in like college, especially because I'm speaking from experience here. If you don't put equilibrium arrows and it is an equilibrium reaction, you will lose points on an exam. So really keep in mind what reactions are super favorable and will always go to completion, and which ones probably aren't as favorable and probably have some back and forth in terms of their reactions. Um, but in terms of like what is equilibrium on a more fundamental level, what I really want to make clear is that it doesn't mean there's no reaction happening. We talk about equilibrium as being this thing of like homeostasis. You're just existing there and you're happy and that's awesome. But that's not necessarily true because chemistry doesn't ever stop happening. Molecules won't suddenly just stop moving and lose all their energy. You're going to keep getting these collisions happening to either form more of C or take C and break it down back into A and B. So it's not necessarily fair to say equilibrium means there's no reaction. What it does mean is that the rate or how much of C you're forming has to equal the rate at which C breaks down. So overall, there's no change in the concentration. So I'll write that down. So what equilibrium really means is that there's no change in the concentration of your reactants and products. And you can actually map this onto like a graph, and I'll show you right here. Whenever you want to do that, you basically just need to understand that over time, these are going to change a little bit. I will lose some reactant and I'll lose some of my or gain some of my product. Um, but what matters is that ultimately they're both going to equal out and not change anymore. I'll just finish writing this first in reactants and products. Okay. So if you want to sort of imagine what that happening, what that would look like when it happens, let's say we have our reactants in red up here, and they start at some concentration. Over time we're going to consume them and slowly lose some of that reactants, but over time we'll reach that equilibrium point where they don't really decrease anymore. And again, it's not because the reaction just stopped happening, but it's because all that product that we're forming, which is forming, slowly, like little by little, it's eventually breaking down back into that reactant, reforming it. So that would basically look like this, where you have your product at here just zero, or it doesn't need to be zero. You could have some starting amount of the product, but it'll slowly increase over time until it reaches the point where it won't increase anymore because you've already reached that equilibrium position. So this would be our product in blue. And based on the definition that I gave you of equilibrium being this position where the reactants and the products are being formed and consumed at equal rates, where would you imagine on this graph is like the time point for when equilibrium begins, would you guess? You can go ahead and pause. I'm figuring out how to do this in the best way possible. But again, it's the point at which your reactant stops decreasing and the product stops increasing, which, granted, it's a very ugly graph. I try my best, guys. That would be like around here somewhere, like around this position is when equilibrium happens. You know? So that's one thing that I think whenever you're doing your notes or like a practice sheet, just like repeat to yourself that equilibrium doesn't mean no reaction. It just means the products and the reactants aren't, their concentrations aren't changing anymore at a given temperature. That will become important later on when we get into more of the thermodynamics of equilibrium. But at least for right now, just keep in mind that equilibrium values, whenever you talk about it, it's always at one temperature, unless you're changing it to study then how it becomes more or less favorable. Okay, awesome. So now that we've done that, we can go ahead and actually talk about like the math of it, which, math kind of sucks, but we do what we do. So I want to first just talk through what I was giving on the previous slide about this A, B, and C thing. And I'll give you this one down here with this fourth one also. It doesn't really matter. You'll kind of see that equilibrium constants and how you use concentrations. Those really don't matter. It depends on what the problem gives you, basically. So this K constant here is called the equilibrium constant. So this is the equilibrium constant. And this is basically what you'll be given for any reaction um, whenever you need to try to solve this. And basically what this equilibrium constant does, or what it tells you, is that it describes how favorable forming your product is. So for very high values of K, that means you're very likely to form a product and then you get a lot of product formation. But for other reactions where K is a lot less than one, it means you don't form as much of that product and you get a lot more reactants staying unreacted. Now, I will say also, that is not to say that a high K means a fast reaction. There are plenty of examples of reactions that have very high K values and that will form a lot of product, but they're incredibly slow to form. If you want an example, I believe N2 and hydrogen to form ammonia, or like the Haber-Bosch process, which is an incredible reaction. It has a weird history, but that's a reaction, for example, that the K value is great. It's amazing. It is a very favorable reaction, but it's very slow because nitrogen is not a reactive element, a reactive compound. So it's very slow to proceed. So equilibrium and kinetics, while they are related, do tell you different things. Kinetic equilibrium will tell you, will this happen or not? Like will I get product or not? Kinetics tells you how fast will you get that product if it will happen. So that's kind of the big difference. I say that because kinetics also has Ks, but they're lowercase Ks. So I want to help build that like differentiation right now as opposed to later. But yeah, basically what you do for an equilibrium constant, it will be some number, and what that number equals is, and I'm gonna try to write this as clear as possible. Given this equation I gave you of A plus B equaling C or forming C, what equilibrium constants are is the concentration of the products. So in this case, concentration of C taken to the power of their coefficient. So this little c right here, if it was a 2, you would put a 2 here. If it was a 3, you put a 3 there. If it's a 1, you put a 1. So it's the concentration of that product taken to the power of its coefficient. And then the denominator is the reactants, but the exact same thing. So it's concentration of A taken to the power of A's coefficient times concentration of B taken to B's coefficient. So, or written out, in a much more simplified manner, it is you can think about it as concentration of products divided by concentration of reactants. And you can kind of see why when I was talking about high and low values of K, why that would make sense. Because like if you have a very high value of K, it means you have a lot of products and very little reactants. And if you divide by a small number, you get a much bigger number. And same is true for the opposite, So that math then lends itself to that sort of expectation. So you always want to check like, does the math and the equation make sense for what I would expect to happen? And fingers crossed, everything lines up correctly and it does make sense. But that's not always true, Sometimes it won't, and you have to explain why this doesn't line up with what I'm thinking. That's kind of the beauty of chemistry that I always talk about. And then to give you like again a wider or a more generalized equation, let's say A and B do some weird stuff and it forms C and D. It forms this other product somehow. Maybe A and B combine into this weird intermediate, and that breaks apart into two different things. So in this case, it's the exact same sort of approach or setup, in that the numerator will be the concentration of our products. So that is concentration of C and a concentration of D, and then taken to the powers of their coefficients. So I'll have coefficient C there and coefficient D here. And then the denominator, exact same thing. We'll have concentration of A and the coefficients. Concentration of A to the coefficient of A times concentration of B to the power of B. This is one thing that's like, it was annoying the first time I had to learn it, but like, again, just like keep writing it down, keep looking at it, and keep explaining to yourself why it is this way. Why are the products on top? Why is the reactant on bottom? That might be a bit hard of a question to answer if you're like in high school right now learning this stuff, but just ask yourself like, what is equilibrium? What goes on top? What goes on the bottom? What is like the number and what's like the power? Like sort of that stuff. And now when you do practice problems or exam questions, you don't have to spend so much time worrying about, oh, did I write this down right? That sort of thing. But yeah, this is basically how you would go about writing the equilibrium constant of doing the products over the reactants. But one thing that you'll notice that I wrote this with aqueous at the top. All aqueous means is like ions in a solution of water or whatever. So you can either talk about ions like dissolved in water or dissolved in some solvent, or you can talk about gases in like a chamber, like we did like in the whole gases unit, which we can talk about now too. But with equilibrium, you will basically only ever work with it in aqueous solutions of ions or gas molecules in a chamber. To be honest, I don't know all of the hard chemistry on like why only ions and why only gases. We'll talk about that later. Um, but something to keep in mind, you will basically only work with aqueous things and gases. Um, so if you ever had to use pressure, for example, it's really the exact same thing, just with pressure, basically. So similar to what we did with the reaction with the equilibrium constant for the concentrations of aqueous things, for a gas, you want to say then the partial pressure of your products taken to the power of their coefficients. So the partial pressure of C taken to the power of its coefficient times the partial pressure of D taken to the power of its coefficient, and then you divide that by the same exact thing but for the reactants. So we get the partial pressure of A to the power of A times the partial pressure of B to the power of B. And like honestly, all the time, you don't always have four things in your reaction. Maybe it's just three, like with A, B, and C. In that case, you get rid of D, or maybe you have A breaks up into B and C. In that case, um you get rid of one thing, like this is just me giving you the very general like building blocks for these constants. You really do just like use whatever the problem will give for you though. So always keep that in mind. Like you shouldn't be looking for four things, like four different molecules to put into this equation. Just use whatever the problem gives you and then just go from there basically. And I will say also, this is technically in units of pressure. Um, And then when I say units of pressure, I mean like these partial pressures are like, they're all ATM, they're all bars, they're all kilopascals. Um, it actually ends up not mattering in a way. I will always admit when I don't know something, I don't understand the unit cancellation portion of this. Um, so out of my own common practice, I always converted my units into ATMs and bars. I don't know if that actually mattered at the end of the day, but I think just out of being safe, I think it is best to convert all your gas units into ATMs. Specifically, if you're in bar, again, it's close enough to ATM to where you can get away with that. I would be worried about using like millimeters of mercury or using like pascals or something. So keep that in mind. I'll write down, I would say like try to use ATM when possible. Um, and then kind of similarly for the equilibrium one that or like the aqueous products one, these are all in units of molarity. So you cannot use moles, you cannot use grams, you cannot use any of that. You have to make sure that you're in units of molarity for all of these reactants and products in order to get the right equilibrium value. And we'll talk about why actually, it's funny enough when we talk about Le Chatelier's principle and how equilibrium changes in response to your system. It is interesting how these do come up again. Um, that being said, while the pressure and the equilibrium and the aqueous equilibrium one will give you the same overall pattern. That being, they will both say, "Oh yeah, you need four more products," or "Yeah, you need four more reactants," or whatever. Um, you can actually interconvert between them because they won't be the exact same number. So if you ever had to, and like, I'll also say this is usually actually I'll change this. This is usually referred to as KC instead of equilibrium. An equilibrium constant can be anything. It doesn't, it's just a very general thing, but this is commonly called KC, for concentration. So if you want to interconvert between them, we have to say that Kp is equal to Kc, and then you multiply this by RT, where RT, sorry, we'll say this, T equals Kelvin, and R is equal to 8.314 joules over mole Kelvin, right? So we have that. However, with this RT term, we have a delta N in the exponent. And what this delta N means is that it is the moles of gas product minus the moles of gas reactants. So if you had like let's say 3 moles of gas in the product and only 1 mole of gas in the reactant, then this delta N term would be 2 here. On the flip side, maybe you have one on each side, in which case it's 0, which then gives you the really funny case because if the delta N is 0, this RT term is just 1, in which case KP and KC are the same thing. So really, and that's kind of what the reason I point this out is because what you notice then is that all KP takes into account is how gas changes. So it tells you if you gain more moles of gas on one side, what should your response be? But there are cases where KP and KC will be the same thing. Um, so like I will say like these both work. So these both work great. Just use what problem gives you. Because here's the thing, after the gases, that we just covered, you can go between either one of these, right? If I give you the concentration of a gas, or no, sorry, you know what? If I give you the pressure of a gas, right, in a certain size um, container or whatever, and I give you the temperature, you can use ideal gas law to figure out the moles of gas in that system. And then molarity is just moles over volume, um, which I'll write here actually. So this is moles over volume. So yeah, if I gave you like the pressure of a gas, you could figure out its molarity for sure. But you're kind of wasting your time at that point. And with exams, your goal should be to get as many points as possible. So just keep the problem as simple as possible and just work with what you're given in the problem. So whether it be Kp, Kc, it doesn't matter. They're both equilibrium constants, and it will tell you if you make a lot of product, or if you make a lot of reactant, or if you make neither and the reaction sucks, you know? So just try to find whatever is easiest. And that's my best piece of advice. While it's good to figure out what works best for you in chemistry, at the same time, keep an open mind and always ask yourself, what would be the easiest thing to do to save myself the most time? That's kind of the best way to approach problems on an exam. So yeah, I do want to point out though, there are other Ks. There are so many Ks actually, and I'll be making a video for all of these at some point. But there is KSP, which refers to solubility products. And this refers to like if you have metal compounds. I think a good example is like calcium sulfate, or like lead hydroxide, lead 2 hydroxide. These are compounds that are horrible at dissolving. We talk about metal compounds. Some that dissolve really well, sodium chloride, that's table salt. It dissolves amazing, right? So, or like a lot of ammonium salts are used in like in ice packs and stuff like that. So there are a lot of metal compounds that dissolve really well, but there are others that hardly dissolve at all, you know? And we use solubility product to describe, okay, if you have this really crappy metal, but then you add something to it, how would that impact it? That's what it's really good for. And then similarly, we have equilibrium for acids and bases, where of course, because chemists are not original and we're not funny, we just call it Ka and Kb, for acid and base. Literally it. Um, so it's just a funny thing that we have so many Ks. And I think some students try to like get caught up in like, oh, like, so I have a Ka problem, which means I'll do this and I'll like find this value. I don't think that's really helpful to be honest, because like K is K, like equilibrium is just equilibrium. Just because you have a Ka doesn't mean you'll have to like square a term, or just because you have Kb doesn't mean you'll have to like divide by four or whatever, like it's not like there's a predetermined like strategy that you have to follow to get the right answer. I think it's just better to view equilibrium as a whole from a more general and like zoomed out perspective and just say, okay, I have these values of this concentration at this volume and this temperature. And I did this change. What should I do? I think that's a more helpful way to go about equilibrium that helps you do any problem instead of just doing like this one specific case. And again, I'll do like some practice problems to show you that. But just like keep that in mind for right now too, as you like move forward in equilibrium and into other chapters of chemistry. Um, and yeah, basically, like the last really important thing I want to talk about then is interpreting equilibrium values. So, equilibrium values are always temperature dependent. So, I'll write that down. So, they are temperature dependent, meaning that an equilibrium value, like let's say you have a reaction and the K value is 1000, right? That doesn't really mean anything. Well, sorry, that does mean something, but it means something at a given temperature, right? Like if I tell you the equilibrium value is 1000, that means you get a lot of products, right? Because if the equilibrium value is above one, that means you make a lot of products. Actually, we'll go back to that. Let's do that. So I told you that equilibrium is this, right? It is KQ is these products over the reactants. If you have a reaction and it goes to equilibrium and KQ is one, that means numerator and denominator are the same thing. It means you didn't make one or more of the other. They just ended up being the same thing. If KQ is really high, you made a lot of this. You made a lot of product, which usually is pretty good. And if KQ is a lot less than one, if it's like 0.000 or whatever, it means you made a lot of this, which usually isn't good, which means you had a reaction that just stayed where it was for the most part, or even consumed some product that you already put in there. So I want to say that now before I get into the actual like value interpretation, because now when we say KQ is a lot greater than one, that's pretty arbitrary. Do you mean 100? Do you mean 1,000? Do you mean 10,000, a million? It's all relative, really, but generally speaking, KQ, once it's over one, it means the products are favored. Wow, I can't find this. I can't find this pencil right now. Products are favored. So this usually means that you will proceed pretty easily into the products. That everyone has their own like preference or opinion on like what a greater than one value means to be significant. I mean, I think commonly like I'll go off of like 10,000 or even 1,000 sometimes. I'm like, okay, it basically means you only have product left over at that point, but it is pretty arbitrary and technically you never have full completion. We just assume it for some problems, make it easier for like the math and for the chemistry. And then the opposite is true for the second one. If you have a KEQ value that's a lot less than one, granted, never negative. Wow, I brain farted. Never negative. You can't possibly have negative. You can't have negative pressure or negative concentration. That'd be really crazy. But if it's a lot less than one, this means that the reactants are favored. Dope. And then lastly, the one weirder case, if you have a KQ that's just one, that means you don't favor anything. So neither is favored. Now, I do want to say KQ being one does not mean you're at equilibrium. Okay. That's not what it means. We will get into that in a later video, but the ratio of two things, if the ratio of of this K value to something else that we'll talk about is equal to one, then that means you're at equilibrium. But a lot of times, um, like students will say, "Oh yeah, the equilibrium constant was one," or they'll get a question like, "When do you know that you're at equilibrium?" And the answer choice will be when the K constant is one. And I'm like, no, I get what you're thinking, like I get where your brain's at, but like it's not technically. All that means is you won't form more product or more reactant. They'll both just stay at the same thing, right? They're both favored. Um, so yeah, that's like the three cases you really care about for equilibrium. Equilibrium, it's just one less than one or greater than one. That's really it. And then there is one very important rule that I kind of alluded to earlier, and that is what you put into equilibrium. So I'm gonna write this in like blue just to contrast it. You only put gases, oh, only gases and aqueous things. So aqueous molecules are included. You do not put any solids. You do not put any liquids. All right. No solids or liquids. All right. Um, there are reasons for this. Again, I'm not the biggest expert on it because it never made sense to me. And no matter what textbook I read or what internet explanation I found, none of it really made sense either. For those who care or those who want to maybe see if they understand it better than I could, please tell me if you do. It's because their reactivity is one, um, which basically means that if they were included in the equilibrium expression, they would just have a value of one, which wouldn't matter then since anything you multiply by one is just itself. Um, I think what that probably means is that like because solids and liquids, because those particles have more interactions with each other because they're in like a lower energy state, I think that means that they're kinetically speaking, they don't move fast enough or have enough energy to contribute to the reaction. Um, I don't know if that's true. I'm really just guessing here based off what I know of chemistry. But that's my best guess is that like because they're so low energy, they don't do anything like favorable or don't contribute anything to the reaction. But again, if you find something online that like says it very clearly, like please let me know. I would love to like finally have a reasoning behind saying this. But yeah, that's basically all you need to know in terms of like an introduction to equilibrium and writing equilibrium constants. Please watch the next video where I go through all the practice problems. I think those are really helpful in terms of building an approach on how to solve these problems and how to justify your answers. So yeah, if you have any questions, like please feel free to leave them in the comments. And yeah, definitely check out any other videos that might be helpful for you. And yeah, just have a great day. Thanks so much.